one on here. Okay. Yep. Okay. Well, welcome everybody to this little workshop that we're gonna do today. We've just seen a fantastic lecture that was super valuable, I think, to all of us. I imagine. We want to try and go a little bit into detail on what seem to be trivial matters. But are in fact not. And I'm happy Ed already painted the big picture and treated everything from salt effects on crops, on soils and management practices, how to deal with everything. But this all assumed knowledge on the levels of salinity of your soil. And whereas if you've done this your whole career, maybe a little plant can tell you what is the soil salinity levels. I am unfortunately not there yet. So for us mortals, we maybe have to actually measure sometimes the soil salinity. And that is what we're going to do today. And the essence of it all is that there are different methods to measure soil salinity, and they are often not reported. And we are going to see what the correlations are between those. But first of all, I skipped the most important thing. My name is Bas. That's not the most important thing, but just the introduction. My name is Bas Bruning. I work for a company called the Salt Doctors, and I'm going to do today this workshop with my colleague Andres Parra. So we both work for the same company. And maybe if I can go to the next slide. You know how? Should I point in a certain direction? Or?
No. I will start and then it will start.
Yeah, so just one little slide of some background, what we do as the Salt Doctors. We create opportunities for salt-affected farmland. So we try to do what Ed is doing, what he told us a lot about. We have three, let's say, key focuses within the company. We do salinity assessment and mapping of opportunity. We do research, training, capacity building. So things we're doing now, train people on how to measure salinity, train people on what are salt effects on soils and crops. And we develop and demonstrate what is possible under saline conditions. For example, using these raised beds or the drainage tunnels, or using mulches, or different tolerances of crop species or varieties, even if we can. So it all started in the Netherlands. Here you see an aerial photograph of a test field. It looks a little bit like a checkerboard. There's some that really stand out because there's nothing there, because it was the highest salinity level that we irrigated our plants with. It was a randomized block design of 56 plots. 56 is 7 times 8. We had 7 salt concentrations from freshwater to seawater and 5 intermediate levels. And all of those were replicated 8 times. So that allows you to draw very nice Hamas-Hofmann curves that we've seen earlier. You have some points at below the threshold level, so where the salinity increases, but yield doesn't decrease yet. But then comes this point after which salinity decreases, and we are also interested in how fast it decreases after that. So that's where our company kind of has its roots, its origins. We both worked there at the time as researchers. And then more and more, as we learned more, we started to focus more on foreign countries where salinity actually is a problem, much more than it currently is in the Netherlands. So we started implying these things in all kinds of countries where you see photos of, I'm not going to mention every country, but yeah, also doing these things that we're going to do today. Today, we also would have preferred to do it in the field, but we couldn't. So my colleague went to the field near his hometown here in southern Spain, where soils are affected by salinity to different levels, which is very relevant. Salinity is not black and white, as we've also heard earlier today. It's not saline yes or not. No, there's a whole range of levels of salinity, and it's very relevant where you are in this spectrum from 0 to extreme. And hopefully I think Andres went to sites to kind of select very highly saline and intermediate and maybe low salinity affected fields. But we will see that, well, shortly, maybe not, but we will try to see that within this workshop. This is an example of the salinity assessments, kind of desk studies. This was for Chile, I think, and Morocco. But we've done many of those, and this is the training thing, and this is more us doing it ourselves. But that's a bit the background of the company, not really what we're here for today. Today, we're going to do a bit of theory. I'm going to tell a little bit, but I think I should keep it short because the hands-on work is nicest. And also when we get the results in, since we're going to compare different methods with each other, it's also be nice to have time to see what is the relation between one method and the other method. And if that is kind of a linear relation, that is kind of what we're trying to get into. And if we fail that, I will have graphs, photos, we will see them in the slides that do show the right correlations. I skipped some?
It was me.
Oh, no, I turned it off. One back?
This one?
Yeah, yes. Today a bit of theory, practical work. So the next one?
This one and then this one.
Yeah. Yeah, so the thing is what I've skipped and what I won't go into, but soil sampling may sound even more trivial than just measuring soil salinity, but that's not trivial either. So we do it often. We take several subsamples of a field, and those subsamples together make one sample. And depending on your visual inspection, what we've seen fantastically today, you may see patches that are different, or one half of the field is different than the other half, or based on the weeds that are growing there. First, you have to look around and get a feel of the field to determine how many samples you want to take. But every sample is at least made out of 10 subsamples, and this is because so you take several subsamples, you look at variation in the field, you look at the crop performances or different weeds, and you focus mostly on the root zone, let's say the first top 30 centimeters of the soil. But recently, the FAO has a new standard that you also look at the 30 to 100 centimeter. So that's what we're doing as well in our assessments these days. And it makes sense, of course, to look at the subsoil, not just for the salinity, but also to see soil structure, or if you can see layers of where your water level is, your groundwater level. This is me not peeing against the baobab, but it's me taking a soil sample in front of a baobab. That was in Senegal.
It's me.
Okay, this is the third slide, huh? The next one. Yeah, I think we skipped now. So all the Egypt stuff is out, but this is good. Andres, could you maybe quickly say something about where you took? Can you go about one back? Can you say something about where you took the samples?
Well, hello everybody. Well, this is well, actually it's a family farm, and this is a citrus farm. It has like about 20 hectares of citrus, and it's quite it's a productive farm. But we have found like several areas where salinity has become an issue, no? And even like in this like round that you can see that there is not any tree. Like well, with some sample, let's see how it is the salinity today. But the thing is that well, in the south of Spain we have many areas as like this example, like pretty fertile or like productive areas, but farmers are living with salinity and other stresses as like water scarcity or like soil fertility, or like even the market. The market is also a stress for the farmers. But so it's like what our farmers are dealing with on the daily basis. And yeah, we have there are about 20 hectares of oranges, 20 hectares or 10 hectares, yeah, so it's like 10, 14 hectares of fruit trees. That according to the literature, maybe if we just look at the FAO references, or we will think that any crop or would be growing there, but yeah, to be like in the real farmer life, it's like we can see that sometimes with several strategies, still you can become more productive or maintain certain productivity. And this is about the farm. And then on the other slide, Maria. Well, this is with we use drip irrigation, and the water quality is about 40 Siemens, that it's not really suitable for the irrigation of citrus crops or fruit trees. But
yeah, so that's what you can see here, but you can't really see it. But
yeah,
you like, see the irrigation level is 4.
So it's about 40 Siemens, and we would like to use a better source of water, but we don't have, and that is like what we had since maybe 6-7 years ago. Like that is the average productivity of the water of the farm. And this, well, I took also a sample on this area that was an abandoned saline marsh that, well, in Spain there are a lot of, there are a couple of them. This place is like about 34 hectares, and I love to put it into to make some kind of activity and produce alopines, and because now it's an abandoned land, and as we already also mentioned that an abandoned land, it's like not like it's gonna be every time worse and worse. So that is like the aspect. Now we have some salicornia, or some alpine species growing there, and it's pretty near to the sea, and we have a shallow water table. And but the thing here is that we can find like this type of areas to make proper saline agriculture in many places all over the world, and somehow these places remain abandoned, and then not many people get, I don't know, the motivation or maybe the strength or to do some like farming activities on these saline areas. And well, I think that might be possible, and it's like we have, or as you have seen these days, we have several options to look at that. And well, I don't know, this is about the sample areas, and if you want to continue.
Yeah, so this is, I thought it was before, but a little small example. I will go through it fast, but about the heterogeneity of salinity. It can be very spotty and very patchy. We've already seen that based on the crops of the photo of Andres and the photos of Ed earlier today. But this is a little example of Egypt, and this is why we take several subsamples to make one sample, so you don't accidentally sample a super salty or the only fresh, you know, little mountain where the only sunflower was growing, and you think, oh, what was the problem? So this is half a fadan. The fadan is, well, let's say half an hectare, 0.42. It's the size unit that they work with in Egypt. So less than a quarter of a hectare. First, we took four soil samples, made of each 10 sub-samples each. Cool. So here at first I saw this half fadan. I thought, okay, the big one here, there, based on kind of what I saw in the plants. And then we saw this. So here it had high EC value, but this is an EC 1 to 2, and this is going to be the essence of today's thing. But in your head, you have to multiply this with, let's say, anything between 3 and 5, depending on the soil type. But this is, I will go into more later. But yeah, an EC 1 to 2 of almost 7 is very high. And then the other ones seem to be rather similar. Still very high, because this is either 10 or something like 15. Very high, but this is almost impossible to work with. This maybe you can still do things with. But because of that variation, I thought, all right, let's divide it in even 12 sections. And then again with the EC 1 to 2 values. And you see that here, this one was 16 and this one was 2.5. So extremely patchy. Here, 2 again, there, 10. Extremely patchy. Later we even divided it into 16 subsamples just to get a kind of a feel or what could be the source of the salinity and the source of this extreme variation within that plot. The 16 thing happened after heavy rains though, so then it was much more uniform, so we had to wait again another month for this weird patchiness to come back. But anyway, it's not the point of today's thing. It's just the message is it can be very patchy, so be aware of that. So the essence is measuring soil salinity seems straightforward, but it's not necessarily is. People use different methods, and they don't even always report on which method they use. And also, as Maria, I think, has talked about, but it will soon be published by the FAO, the INSAS, that even countries have like different traditions in how to report soil salinity. For example, the Netherlands, the country I am from, is kind of a weird exception, I think, because it's water salinity, not soil salinity, but water salinity is always reported in milligrams of chloride. That's how all the water boards work with. So then you have to try and translate milligrams of chloride per liter to EC values or to sodium levels or to millimolars of sodium chloride or whatever. Other examples that we've seen, so the one is this chloride concentration, it's like here, but the ECE value, that is the standard, that's the holy grail, that's what we're trying to get towards, that is the one that Ed correctly all the time used during his whole talk. But as we will see, it is more laborious, it takes a bit more skill, a bit more even fingerspitzengefühl. It takes a while to get it in your hands. I think. Yeah, my pronunciation probably was bad, but anyway, then there's people that use 1-to-1 ratios, 1-to-2 ratios, 1-to-2.5, 1-to-5, 1-to-10. There's so much out there. There's sodium chloride concentrations, which more comes from the lab, just in millimolars, because that's how you make your solutions. Just sodium concentration, just chlorides. Also TDS, EC probe is one that we will use today. People use sensors. But we want to be reporting the ECE because that's a standardized thing that we all can do. And because the amount of water you standardize, that is the essence of the making a saturated paste, but we will see. Because you standardize the water content relative to the soil structure, it is, yeah, you can use it in a clay soil or a sand soil or here or in Australia or in Spain, or it should be universally applicable, and it should give the same result irrespective of soil type or things like that. So what is it, an ECE? Mostly what is that E standing for? So the EC stands for electrical conductivity. So what we're measuring is the resistance of an electric current through an aqueous, watery solution. So it is the electrical conductivity of an extract of a saturated paste. It has to be an extract because you want to measure it in a watery solution. Almost all EC meters measure in the water phase of a thing. There are a few exceptions. Well, we brought one exception. There are sensors that can measure in a soil, wet soil, but that is super sensitive to water availability. So by making a saturated paste and then use this probe that you can measure directly in soil, you can still kind of standardize the amount of water that you've added, but it is not the most accurate method, especially not under field conditions when you don't know the water content. But if you can make a saturated paste in the field, which you can do, and you know the correlation of your probe measuring device and how it corresponds to actual ECE values, it can still be a valuable thing. But again, the water content is super important. As Ed also said, you can put that probe in a bag of pure salt that you buy in a supermarket and it will say that there's no salinity, because the water is just as important as how much salt there is. But that we've already heard. So you need to make a saturated paste. That's going to be the main aim of today. And well, we have 5 samples. One of them we will use to make a saturated paste. Us to show you. And then, yeah, there's 4 other people here in this room or in little groups that can make also a saturated paste. There's a list of attributes, characteristics, traits that a proper saturated paste has. It has a glistering surface. It should slide off your spatula. If you tilt it and leave a clean spatula, this is what I call a spatula. The things we will use for that today. But this for me is the main one. If you have you have a dry soil, the 5 samples here that you've seen are completely dry. And here we have demineralized water. So water with nothing in it, and not very little salts. So we start adding water to our soils, and we steer until it becomes a nasty clay kind of, muddy mud. We're going to make mud today. That's basically actually it. But then if you have your mud and it has a glistery surface and it slides over your spatula, the most important thing for me, you take your spatula and you put it on the bottom of your container, and you make one stripe, a trench, whatever, and then you remove your spatula. It should stay. But as soon as you start tapping the side of your little container, then it should close. You can see that. And then your sample has taken up all the water it can take, nothing more. So if you would add water, it would fall down at the bottom, let's say. So ideally also, if you're very brave, if you make a good saturated paste, you can put it upside down on the table or on your head if you're really brave, and there should nothing come out. But let's see, we have people brave enough here today, but let's see. Now, then you've done that and it looks like a saturated paste. The protocol asks for leaving it for 24 hours. We've done quite a few tests. It doesn't usually change so much if you do it after half an hour or 24 hours still. That's what the protocol demands, and maybe some other people have other experiences. Now, and then comes the tricky part. Then you need to extract your water fraction from that saturated paste. Sorry. And there are several ways you can do that. You can use centrifuges, like many labs have centrifuges that will take tubes like this, and then you will separate your whatever soil fraction from the water fraction. Usually enough, even in that tube, to put an EC meter in. You can use vacuum pumps. You can use a compressor. That's what we usually have, because we have a device that uses a compressor. Anyway, all things that either are very expensive or very heavy, and things that we cannot have with us today. So we can't extract the water from the saturated paste. And it also, these are either expensive or bulky or take time, and it's 24 waiting time. And it takes this experience and it takes more time. So that is why the ECE is favored, because it is more, it's what should be published on. It's more like the standard for publishing, and how also people know how to interpret that number. But yeah, it's laborious, and it requires equipment. So ideally, we also have a method that is simpler and faster. And we saw earlier the EC 1 to 1, 1 to 2, 1 to 2.5, 1 to 5, things like that. Or measuring straight in a saturated paste without extracting the water fraction. That all would be faster and require less equipment, less equipment. However, we want to know then if the result that you get with your simpler, faster method has any correlation to an ECE value, the more complicated method, and if so, if it is also a nice and straight correlation between those things. Now, you can do that by using different methods in the same sample. You can take one sample and apply 5 different methods, and then you can look at the correlations between those different methods. And if you have one field or one soil type, and you've done that 20, 30 times, you will find that you get a very nice straight line. And at some point, you can pretty much start trusting that, okay, whenever I know I use this simple method, I just use this multiplication factor to get to my ECE.
But so we can pass from like an ECE measure on saturated paste to another dilution, like just multiplying.
Yes, but since this, let's say 1 to 2 method, which we will apply today, 1 to 2 stands for 1 volume of soil unit to 2 volume units of water. So let's say you add 10 milliliters, so it's in volume, 10 milliliters of soil, and you add 20 milliliters of this demineralized water. And then you shake and you wait a bit and tal. We're going to do that. But you add quite a bit of water because EC meters want to measure in a watery phase. So you add quite a bit of water. And ECE, a saturated phase, has considerably less water. That's why you can't stick an EC meter. So you'll find that almost always the simpler methods, well, almost, yeah, always, except for the probe where you can stick directly into a saturated phase, that they are more diluted. So they will give a higher or lower value than your ECE. Okay. What do you think, a higher or a lower one?
On the saturated phase compared to
no, yeah, so if I do a 1 to 2 method in the same sample as an ECE, will the 1 to 2 method give me a higher or a lower EC value?
Lower compared to the
ECE, correct, yeah, because you've diluted it with more water.
Yeah, because I've seen that a lot of data sets have like saturated phase and like other dilution. So I would be interested to create a data set that is homogeneous, but I've seen from my brief research that in saturated phase, you have just a quantity of water that basically you don't know. So it's difficult to pass from saturated phase to other dilution, like being very precise.
Well, I will show you some correlations later, but generally what you're interested in is your ECE. So I don't really know the need to go from an ECE to EC1 to 2, but I think Ed has a...
I wanted to just make a point that some of the soils around here are gypsiferous, and it is the one example of a time where because gypsum is sparingly soluble, there is the only time where what you're saying doesn't work is in a soil where there's a sparingly soluble salt. For soluble salts like sodium chloride, it's great because the same amount of salt dissolves in an ECE as in an EC1 to 5. Yeah?
Yeah.
It's the same amount of salt that dissolves. But for a sparingly soluble salt like gypsum, the more water you add, the more salt will dissolve. And it's the one instance that we need to be aware of where multiplying by a factor to get the ECE gives you the wrong result.
Yeah.
But so it's just a special thing for some parts of Spain, I've noticed. But otherwise, we do exactly what you do. Yeah, we do exactly what you do. But for people in the room, just to be aware that there's one special case where it doesn't work.
Yeah.
Those are if the soils are gypsiferous.
Yeah. Okay. Thanks a lot for that addition.
Yeah, another question. Maybe it's a very ignorant one, so I'm sorry in advance if it is. But as you said, there are like different methods and different metrics, which sometimes makes comparability across the world difficult. Is there an ambition from an institution or from multiple institutions or a collaboration, FAO, whatever, to harmonize and standardize those?
I think so. I think that is kind of what the work of Maria I just referred to is kind of aiming for. Also, this FAO standards like, okay, let's focus on the top 30 centimeters and then the subsoil defined as 32 minus 100. So I think there are efforts, but for example, in the Netherlands, this chloride concentration in water is it's a battle people are picking, but it's very hard to convince. How many water boards do we have in the Netherlands? 70 or something to all change their methods after 200 years. I don't know. But,
let's say the approach is also to develop the conversion equations. So that because we have quite many data which has been received during, let's say, 100 of years for different countries. So it should be also safe and used and whatever. So the development of conversion factors is also something. It needs some research because for some soils it can change depending on the soil texture and humidity. So but still it's also one of the approaches.
Okay, thanks.
Yeah, and one thing what Ed said, which we, due to time constraints, will probably not come into, but as I mentioned, EC stands for electrical conductivity. So it is kind of a, a sum, I will say something about that. Not only sodium affects how much resistance an electric current finds from traveling point A to B. All cations and anions play a role in that. So once you know your EC, you have some kind of bulk thing about how many cations are in there, or conversely, how many anions are in there. But after you know that, you also want to know which one is the dominant one. So of course, after you've determined your EC value, your ECE value ideally, you want to know, okay, which cation, we usually look at the cations, is the one causing this elevated ECE. Is it sodium, or is it magnesium, or calcium, or potassium? Potassium, very unlikely, but calcium or magnesium is very possible. Indeed, we find that also. So what we're going to tell today is indeed often applicable, but don't take it for okay, so from now on, I just take a multiplication factor of 3.5 to go from EC1 to 2 to ECE, and it always works. No, not at all. Always try it on your local field, and you have to do it on your sample, and first make all the methods and then determine. I brought tools to quickly determine the potassium, caesium, magnesium, sodium concentrations, but yeah, like I said, I don't think we have time to get into that. But it is, of course, a very important aspect. Electrical conductivity is some kind of overarching number, and then you want to know which anion it is, or cation, because that also allows you to calculate these SARs we've seen in Ed's presentation. That's some sort of sodium absorption ratio, and for that you need to know also the concentration of other cations, or for the ESP, the exchange of sodium percentage, or the cross, or I don't remember what it stands for, the cross. That is one level after this little practical of today. But yeah, I like the question. So it's the more dynamic, the better. So if you have anything coming up, please just ask. So us as a company almost, we usually use this EC1 to 2 and the EC probe if we have to do a quick way. So those are the ones that we brought today as well. Those are the ones we will do. EC1 to 2, so one dry soil volume unit with 2 water units, volume units. You add them, you shake them, you wait, you add, shake again. It's kind of easy and fast, and there's a pretty good correlation with the ECE in 9 out of 10 times with this reservation. Yes.
Wouldn't it be better to do a proportion of the mass instead of the volume? Because depending on the texture, we might have differences. Make sure that fundamentals are standards different mass from the
Yeah, with the 1 to 5 method, I think it is volume to weight is the protocol. Yeah, volume to weight. Yeah, 1 to 2 is volume to volume for some reason, but yeah, no, yeah.
The trouble is you don't have a balance in the fluid.
Exactly, that's the easiest thing.
And you can quickly do a volume.
Yeah,
you're not after the perfect answer. No. You're after an answer. Good is better than, but perfect is the enemy. What I heard yesterday, perfect is the enemy of good. You're not trying for perfect.
No.
You're trying for
certainly. Yeah, and especially with this 1 to 2, I mean, you're gonna have a bit of variation, how much soil you have, how much water you add. So you're adding two sources of error there. You're gonna multiply it with some kind of factor to get an ECE, another, adding thing. But you want to know, am I like between 3 and 5, or am I above 6? So that's kind of what you want to know, with this type of method. If you want to do it properly, do an ECE and determine all the cations, and send it to a lab and get. But this is just to get an idea.
You also don't try it.
You can not do it if you can. Yeah, but then of course if it's very lumpy and it has make aggregates, it's harder to get a correct volume. But yeah, no, you can even do that. But if we do it in the field, we prefer to make an EC, a saturated paste, and stick our probe in. But just that, because we've done that many times, so we have correlations for ourselves. But yeah, for different soil types.
But the advantage is that you can do that in the field, while the 1-2 method you will have to dry.
Yeah.
according to the protocol? Well, you have to, according to the protocol, dry also for the saturated phase, but we have done it and we have seen that at the end it's
No,
it's
even
good enough.
yeah. And for the 1 to 2 as well, like if you dry it, you just get rid of your water fraction, but the salts will be the same. So even if it's not perfectly dry, it doesn't matter. Easy. Oh, sorry. So,
What you said, we are adding our soil based on volume and water, right?
the 1 to 2 method is based on volume to volume. Yeah.
Yeah. But considering the fact that different soils are having different porosity, different soil particles,
Certainly.
etc., there are a lot of factors which are affecting the volumes.
Yeah.
How could we deal with that? Because it changes the concentration of salt in the soil.
Yeah, certainly. Like so, yeah, of course, a coarse sandy soil, yeah, has a lot more air and water spaces than a very thin, yeah, very fine.
Particles are bigger.
Yeah. So there's more, it has less soil surface area than a clay soil with the same volume.
So isn't it better to do it based on the base instead of volume?
Yeah. That's indeed possible, but indeed for this. Then you would have to walk around with your a very accurate scale all the time. And indeed for quick soil assessments in the field, where you maybe do also a 1 to 2 or this thing, it's just faster and quicker and requires less things. And if everybody does it that way, then still you can compare your results with mine because we've both used the same volume to volume thing. But yeah, again, I'm not saying that this is perfect. It's to get a rough ballpark estimation, like, okay, cotton is still possible here, or I have to think about halophytes, or what can I do with my lettuce or my onion?
And the correlation will be different, no? From a sandy soil, from a more heavy soil, the correlation to obtain the ECE will be at the end different, no? That makes also change.
Yeah. Thanks.
I thought I saw another question.
That was actually what I wanted.
Yeah.
Conversion factors or the conversion methods, I know they divide between different extra classes.
Yeah.
To correct that.
Yeah, so this is just a little bit of a visual way to show the differences in practicality of measuring things. This is how to one way of making an ECE, but we are in a lab here and we have tubes and stuff and we have materials. Here we are in the field and we have only one little thing, or here we are in the field and we have also this tube. But this you can do in the field. That's obviously not. That takes a long time. This is fast. And again, we're after some rough ballpark estimation of what are we dealing with here. Yeah, so this goes a little bit in which cation is the one that causes this possibly elevated EC that you're measuring. So EC tells you something about the sum of the cations present: sodium, potassium, magnesium, calcium. But we all know that sodium and potassium have one value, right? One plus, one missing one electron. Calcium and magnesium are contributing more to the conductivity because they have missing 2 electrons. The same goes for the. So yeah, if you know this, that the EC is actually the sum of these things or the sum of the anions, and I know less about it, so I put it between brackets. But I mean, since every watery solutions, as far as I understand, is in balance between its cations and its anions, you can do the same for its anions. We look at the cations. So yeah, I mean, not too many questions out of this, please. But anyway, if you know the concentrations of those 4 main cations, you can also, just by knowing them, you can know your EC, because it is the sum of those 4. You have to express the concentration of these things in milliequivalents per liter, though, because of these different values. What is the word? Yeah, the valence, because these different atoms have atoms have different valence, or +1 or +2. They value differently, so that's why you have to express it in the milli equivalents per milli equivalents because that takes that into account, the valence of a certain cation. Anyway, you express them in that unit and you sum them all up and you divide it by 10, that gives you the EC value of your soil. Usually we do it the other way around, but anyway, as I said, the same can be done with the anions, but what this exercise is for is that you want to know which cation is the one causing my elevated EC level, because it is not the same at all for a plant if it happens to be in a very highly calcareous soil, or if it's sodium that's super predominant, because sodium is the one that has this toxicity when it gets into the plant cells of the above ground shoots. So we want to know which cation is responsible. That's why I brought this thing, but realistically, talking about it with my colleague, we thought, no, we cannot do this with unless. So we probably won't do it. But what we hope to be able to get to within time is to see what is the correlation between different methods. And yeah, I call them parameters because that assumes that also we could measure these things, but let's see how far we can. This went something wrong here. Saturated paste in the photo, extract moisture and determine EC. Yeah, that is what we see there. Here's a little bit, yeah, ignore this graph. Sorry, this last minute's changes in an hour ago, which results in that. Anyway, here we have some correlations of different soil types. So the questions that some of you asked: soil texture, sand or clay. So here we have EC1 to 2 versus ECE in sand, silt, and clay soils. Here we have EC1 to 5 versus ECE in the 3 different soil types. And I'm not sure if it's readable for you, these expressions, y equals 8.8 times x. So we have to interpret that as I take my EC1 to 5, I multiply it by 1 times 8, and I get my, no, sorry, I said it the wrong way around. I take my 1 to 5 x value, I multiply by 8.8, and I get the ECE value. And we can see that for the EC1 to 2, to go from an EC1 to 2 to ECE, you have to multiply by 3.6. But in a clay soil, it is 2.1 in this example. This is just some soils in the Netherlands. Again, do it yourself for your own soil and with your 1 to 2 or 1 to 5 or 1 to 2.5, your preferred method. It's good to make these correlations yourself. But as you can see, all of the lines are pretty straight. It's not lots of dots on these lines, but yeah, the correlations are pretty good. I think the next graph, this one, will have a little bit more dots on it. Not that many either, but a few more anyway. Yeah, I'm in background more ecologist than someone that has anything to do with farming, but still R-squared values of 0.97 is unheard of in biology or ecology, so it's pretty good. Not perfect, but good enough to get this ballpark estimation that we're looking for. So here we're looking at the ECE versus the EC probe. So this is one that we're going to do today, and this tells us that if we get this EC probe value, we have to multiply it by 5 to get to an EC value. ECE value, I should say. I hope by now it's time to get our hands dirty. Yes. So we're going to make a 1 to 2. We're going to make a solution that is called, yeah, well, we're going to do 1 volume of soil with 2 volumes of demineralized water. And this is the protocol for it. So you start with the dry homogenized soil. Many of you have seen that we frantically have already prepared that. So Andres took soil samples, fantastic, dried them. We've been sieving them today here. They are now standing in front of you. So this is sample 1, 2, 3, 4, 5. So this is the one for super highly saline. I have really high hopes for that one. Yeah, maybe we're gonna break my record. I have no idea. But yeah, you sieve it, you homogenize it. And I mentioned earlier that you can take 10 milliliters of soil, but these tubes that we will use, they have a volume capacity of 50 milliliters. So we can use 15 milliliters of dry homogenized soil and add 30 milliliters of demineralized water. Don't add 15 milliliters of dry soil in your soil in your tube and then start adding water to that same tube to come together to 45. That's not the way it's done. You take another tube and you add 30 milliliters of demineralized water to the other tube, and that's what you're adding. That also relates to the sand and clay things. Anyway, you shake well, you leave it for half an hour, it says. We won't have time for that, but we will shake it every now and then. That's also a bit of a sidetrack, actually, that I didn't put in it. But this 1 to 2 method, shaking your soil and then letting it stand for a while and see how quickly your soil settles down again, doesn't only say something about your soil type, because of course sand will immediately separate and hope you have your water fraction in your sands. But if you have more silty, clayey soils, it will also tell you something about the dispersion of your soil. If it stays cloudy forever, it means you have lost your soil structure. It has become impenetrable for water, because clay soils want to aggregate. They should aggregate to these soil aggregates, and they become bigger particles, and then you still have good water infiltration, good oxygen infiltration. On the other hand, if you lose that soil structure because sodium starts to dominate your cation exchange capacity, all kinds of details that are not relevant today, but if that is the case in a sodic soil dominated by sodium, and then pH also plays, but let's drop that for now. But then you lose the soil aggregates, the aggregates of a clay soil. Now then all these tiny clay particles just start floating around alone. And just this dispersion, flocculation, all kinds of terminology. But anyway, if you make a 1 to 2 thing and you wait a half an hour and it's still as turbid as it was from the start, and you can even go home and you leave it, which I often do when we give a week of training or something. Sometimes it is as turbid as it was the next day when we arrive in the lab. And then you really know that you're going to have water infiltration problems. You're going to have a soil with very, very bad water infiltration and oxygen infiltration. Is that a question?
Yeah, so correct me if I'm wrong. I got the feeling that nobody actually measures the ECE, the saturation phase levels, because it's unfeasible to time consuming. So like, why is that the standard?
Well, I think it's standard because it's the most, like, technically you add exactly the same amount of water to your sample. Then if it's a sandy soil, that doesn't matter if it's sand from this beach or from that desert or whatever. But I think the first part of your question, I don't think is true. People do measure ECEs, like, scientists, the people that have access to laboratories and stuff. Yeah, they do. But yeah, farmers not. No.
Yeah. But what I've seen also, it's like in different labs, in different places, is that maybe they use another method, thinking that they want to or they want 5, and they think that they have the correlation, like to obtain the ECE, is maybe if you are using the 1-2 method, it's multiplied by 2 or by 5, and that is done by researchers, and it's not a farmer. And sometimes
I would propose maybe like the ECE 1-to-1 could be a standard.
Can I have a crack at this?
Yeah. No.
You're right. It's difficult to measure. The reason I like the ECE is because it is a salinity that a plant will see if the soil is saturated. And there are some rules of thumb that you can use to estimate what, because it's really the salinity of the soil solution that determines plant growth. Okay. The salinity of the soil solution at field capacity is approximately double the ECE. All right? Because, okay, it's a nice rule of thumb.
Yeah.
And you'll find it buried in USDA Handbook 60 on page 43, and it's buried, but it's a lovely rule of thumb. And the EC of a soil at wilting point is approximately half that. So the ECE actually is something that you can relate to what a plant will see, right? So hold that thing in your mind. The ECE is the salinity of the soil solution when it is saturated. It is half the salinity of the soil solution at field capacity, and is a quarter of the salinity of the soil solution at wilting point. So it is a useful thing still to have in mind because it can help you get a message to a farmer about what the conditions are that the plant is seeing. Yeah. And so I find it useful from that point of view. Otherwise, I agree with you.
Yeah. No, to this, it's the last slide anyway, so I thought I can leave it in because we probably don't have time to get to it. But one of my questions, the advanced ones, okay, EC is the ideal standard, but will plants under normal field conditions be exposed to higher, lower, or the same ECE values? Even though it is indeed something that the plant may actually see, most of the time it is exposed to a more concentrated value than the ECE value. So it's indeed a measure that is relevant to actual field conditions, even though the plant will usually experience higher ones. But yeah, this was kind of the last trying to think about what we've been doing questions, but very nice that they come up. Thanks for clarifying. All right, was I done with the? I think so. So after you shake it a few times, you just use the standard EC meters, which you have ranging from 5 euros to 500 or probably 5,000 euros. I have no idea, but something intermediate usually works fine. We brought a few EC meters, and then you just determine the electrical conductivity in your watery 1 to 2 solution. So let's do it. Yeah, here so it's also this visual inspection. I don't know if you can see it, but here you see that very quickly the full 15, so there's 5, 7.5, 10, 12.5 is sand, fully sand. This immediately settles. So you know that there's a tiny fraction of smaller particles, and the rest is already almost clear of water. So it also tells you something about where am I from between my sand versus clay spectrum at the particle size distribution. If you get more experience with that, it can actually tell you quite a few things. Not just settling time, but also a fraction of different particle sizes. But anyway, this is what it would look like, and I think let's go and start doing some. This is the core. Some more correlations, but I've already went into that. But yeah, again, this one is a bit messier, but all in all, good enough for what we tried to achieve. Then is this thing that we also already went into because of questions, but after you know your EC, you want to know which cation it is that causes your elevated EC. Okay, so this says assignments, but it's first an assignment for ourselves. Do you feel like making a 1 to 2 or in a saturated phase where we can divide, no? Yeah. Which one? Should we take sample 1? Okay. All right. So now we're going to get into practical things, and I hope you all can see it, but later I hope that I can give to some of you one of these things. We can give you those, and you make a saturated phase. As you notice, we kept a little bit of soil separate. Does anyone have an idea why we kept some backup? If you add too much water, you can add more soil. Yes, very good, very good, very good. Yeah, you must have experience. You almost overdo it?
Yeah, that's why I use EC1 to 5 because I always overshoot with the ECE.
I
had too much.
really?
I'm terrible. I don't have enough experience.
Not fingertips, huh? All right, you have here for the 1 to 2. For the saturated phase, yeah, and then I go to make it 1 to 2. So yeah, indeed, it's arbitrary. Yeah, we could have also said, okay, we're going to look at the 1 to 5. Me personally, I like 1 to 2 better because with 1 to 5, you add so much water relative to your soil. I have the feeling you're inflating the error you're adding, but that might be nonsense. I think that based on that reasoning, 1 to 1 might be better than 1 to 2. I have no idea. Anyway, I put too much water already. And I need glasses for this. Unfortunately, but true. I am straight into 15 milliliters. I don't know. Please come and check. Is this 15 milliliters? What do you think?
Yeah,
It is? Yeah. Okay. Then I also need 30 milliliters. I'm going to ask you to check that as well. Of water in a separate tube, not in the same tube as I said. Yeah, put your mics on. Yes, I'm just making the saturated phase. One to two,
Would be the process to make the saturated phase and here extract the water that will give you in the lab the ECE. But this is with the
How much is this?
Bas showed on the previous slide with the EC Pro.
Too much?
Because for us,
Could be a drop too much, huh? Not enough? A drop more. Oh, it's gonna be tricky.
and so we call it the EC Pro.
So when you go measure it directly, basically.
That must be too much.
This is
Too much now.
good approach once that you know the correlation because normally we have a different project.
Now you're good?
And,
Now let me check you. Yes, I agree.
Go somewhere.
These ones can't stand. It's pretty annoying, but they can't.
This is something that they can visit the field on the same day.
15 milliliters of dry, sieved, homogenized soil, 30 milliliters of demineralized water. So two separate tubes, and now we add them together. Now, while you have them, go for it. Okay, now we need a lid. So it's fine. And then shake well. And really make sure that everything is properly closed. Yeah, it's like it. I think you can.
Will you measure straight from the saturated phase now?
Yes. Yeah.
Shake, 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 shake.
Shake, 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 shake for the camera.
Some movements. You can't wake up because yes, it fits very well. Yeah.
And well, I don't know if you think how to do what Bas told about making
Everything, there's no dry part? Yeah. Let's leave it for a few minutes and then we shake it. Let's just leave it in front of this so we know it's that one.
It cannot retain more water, and it's well, just saturated, and this is the point where it should be. Like, well, normally if you can make the trench, but if you put it just like this,
Can you put it
That's for the pros, huh?
if I put it in my head, it's gonna be in my head. You know?
Come on, I'll take a photo.
A saturated head, huh? And
You show the camera the saturated phase.
we measure, we weigh.
Oh, it's difficult.
No, it's good.
It's two cameras.
So this is like just the point at what saturated paste should be. So if we make a trench, both sides should be like a side, and if we like shake it a bit, make it becomes together again.
Yeah, I mean, if you keep it upside down instead of tapping it, it should fall out. But yeah, does it glister nice?
Yeah.
Yeah. Maybe it's nice to do a liquid water.
Yeah, just that's more or less the glister color or
It is pretty much the same. What do you think? Should we first make them all or measure this?
Maybe we can just
Make them all, right?
yeah, understand because if we have to wait, but maybe they can do it.
Yeah, exactly. So are there 4 volunteers that feel like making a saturated paste? And well, we need 8 volunteers. Here we have one. Please come. 2. We need 8 people in total. Yeah, come. Yeah. Yeah, you made one. Yeah, 1 to 2. So you have to make a saturated paste. Yeah. So for now, we can write labels. That is of course ideal, but at least try and remember yourself which sample you're working with. So if you want to make a saturated paste, you can use this one. And do you feel like making a 1 to 2 or a saturated paste? Yeah, everybody wants to make saturated paste.
We'll go from the others. Yeah.
This sample and
So you can smile for the camera.
Just to have we don't have an idea. Like I have this like a tube before, so I put something like 30 milliliters.
Okay, you want to make a saturated paste of this one? Let's just use this container, but then we keep a little bit more for the 1 to 2, and for if you add too much water.
From the same sample.
So we have a little bit more safety backup.
Here we can keep
Because we don't have enough extras to everything goes to the double.
yeah, we can take
It should be enough. And I think unless you said that you almost added the full tube.
no like something like 30
About a third.
I did the same board because
No, this one you can do.
so we will put
And we need
something here.
You can do this one if you want. This one is already been done. You can make a saturated paste with this one. And we need someone else to make a 1 to 2 method of this one. You feel like doing that? No. Yes, you can use this water sample. This is all demineralized water. And you add a bit of this. You take a spatula. This one has been used. And you start steering it well. Yeah. So let's say that he had used about 30 milliliters. So you can maybe start with like 20 or something and see what it looks like. For you, you can take 2 tubes.
Okay, go to smoothie. No. You can make it more.
And you can take 15 milliliters of that.
Coopera, me toca.
15, yeah, steer. Don't be shy. Yeah, you can also just improve it. Yeah, but remember you're working with sample. But yeah, you can add more. You're gonna need
Now you need to add the double amount of water.
For those that are not doing anything but they are interested, you can still come and have a look if you want. And we'll add some for you. Yeah.
Share is the right. We're going to take 1 measure centimeter and then compare that to the ECE value.
Yeah.
Right?
Yeah.
So when you show the correlation, the curve talks to that.
The curve?
Where all
Straight lines.
yeah, you can straight line, but you also back to the audience. I would say
No, but then we get
Very slight associated with minuscule.
nicely.
Don't worry about it. Don't worry about it. For the purposes of this exercise, forcing it through the origin is quite acceptable. The conductivity of pure water is microscopic.
about the fact that we have to make only calibrated, so it was always show something about but not measuring it.
Not the idea, for example, in Senegal, we are working with soil, even in the Netherlands. Also, we need to have like that thing that already the was a 50 soil, and we are now 100 of them. Also, like you feel that
A lot of this have standards and calibrate against standards.
Yeah, if you haven't done it for a while, you just measure your standard. And if it gives more of that, if it's off,
Then you have to change
for example, that hit and then so showed every tomorrow we'll try to calibration, it's super net all the time. So if you haven't used it for half a day,
normally you notice that it's like now well mixed. According to the protocol, we have to let it rest for 15 minutes and shake it again.
I have to check how the guys are doing.
Yeah.
Show have a question? Okay, yeah. Let me have a look at it. 15 and 30, perfect. You're working on the same sample. Yeah, so now you dug a trench. Do you make a trench again and you tap it? I have to tap it way too hard. It's not blistering enough. Okay, do you know which sample you have? This is fine. Okay, this is the coolest one. If you're going to use the original, let's keep a bit more safety and you can start by how much do you have? But I think do you know?
No.
You have 4. You have 5. Okay. Perfect.
Well,
yeah, but we ordered some in cubes, so it's easier to afford. But it's the same. Good. This one also needs some more shake.
and the couple samati camera. Well, here everything.
How is this one going?
Okay. You know this one.
Yeah. But yeah, it needs more water. Usually, if you shake it, it should pretty quickly become uniform. But yeah, we have a trench. They stay nicely, but with this light tapping, it should start close. It's really close. It's really close. It starts to have this nice glistering. A little bit more water. A little bit more, but don't overdo it because it's very close.
Yep.
If the soil is saturated and you tap it, it tends to become more liquid again. Like on the beach, you start standing. If it's not enough water, it will stay. It's like till the beach water. And if it's too much water, the drain will not stay.
With mud? Like blending with mud?
So we like doing saturated paste as well.
Yeah.
Over the endpoint.
You always use 1.5?
I always use 1.5. And then we it depends on the texture. Yeah, it depends on the texture. So the pack, well, there are published. I use the format. Yeah, no, we just use the format.
We've done it right.
Yeah, but I like the 1 2. I always worry 1 field, 1 5 in the field is wrong. But seeing you do it with the poly at then poly.
Yeah, you can't use the same cube.
No. That makes the take home today.
That's great. It's Great, look good. 14. No, we're good.
Yeah, we have one, but
Thank you. Yeah. you can look nice and history. This looks nice. Yeah, it stays. It's not filling with water. I step with lively. I think it's pretty good. But let's ask Andres. Andres is better than him. It doesn't slide on the spot. That's one of them too. It should slide on the spot. I think you need to drop more, but let's ask Andres. Let's ask Andres. One maybe one more. Nice. It doesn't slide on the spot. But, can you do the French again on the light tapping? Oh, sorry. So you make a trench, you put it on the bottom, and you do one straight, and then you slightly tap. Maybe a drop more, eh? Yeah, it's pretty close. But also like it's there. Good enough. Like if you put all together, it becomes you want to try with your hair. It's going. Yeah, now you're very yeah. You know is there already 1 to 2 of this sample? Did someone already made a 1 to 2 of this sample? Maybe not. This is sample 2.
Yeah. And then normally, like what we can do, like because well now we are here, we label that we don't have no mistake, no mistake.
So you had sample too? The second one? Yeah, you took it from him. Yeah, I think it was the second one. But I thought that and also if someone can make a 1 to 2 of that one. You can the other method, this method. The 1 to 2. I'm pretty sure this was sample 2. Good one, a bit wet. Can you make the trench? Not staying, you see?
Normally, we will let it rest, but measure. We don't want to touch it now because we want to measure.
Yeah, we do.
So we will try to let it in this position. Steering now. You know where we can just place it on. Yeah.
So this is sample 2. We're starting to lose.
I think we need to mix it.
After adding,
Sample 2. So we will
sample 5.
Then we
Right.
and then we need to make the sample 1.
Someone else makes a bit of a road. Someone else comes along and drives the car, and the road is getting wider.
We run out of 1 to 5.
Maybe it's like if we can use something.
We have half an hour that road.
We can see it's there. The other one,
We will do normally.
Simple one, like.
Yeah.
Spatula.
Yeah.
Bas, I'm sorry. You're in front of the camera. Sorry.
So this is what that is why it's important to keep some soil for the samples. So because you can count check if we have enough.
Yeah.
Why is it so high? Because the salt crystallized.
The weight or the weight? How much weight? I would say that you can it's not like you
need some oil.
It can be it doesn't matter.
This one getting no, this one. Someone make this.
Quite heavy.
It feels like making a 1 to 2 red. 1 to 2 red. Someone make a 1 to 2 with this one. Can you do that one?
I got the project and they pay on
I think this is sample 3. I think it still needs both.
Yes,
but it's getting quickly out of control now. What is this? Sample 2, right? Yeah. And this sample 1 was to yes, I don't do that. On sample 3, yes, you're working on sample 5, eh? And this is 4. 1 to 5. Can we make it there so it's with the order? This is 3 they're working on now. And what's this? Sample 1. They're working on 3, 4 should be here. I keep shaking every now and then. Like we will thank you. Different tune. First 15 milliliters. 1, 2.
Yeah, I have never done it myself.
Dear colleagues.
Hello. So we have our remote participants. So for them, we will now proceed with the measurement. So we make a short pause.
Okay.
With this fast-paced preparation.
Yeah.
Then we show the measurement.
Okay.
And then we make
the correlation.
Easily disconnect.
Sure. We will be done with this in 5 minutes.
Not an interactive program.
I understand. This is 4. So now we're pretty much. We don't have. If you shake that one, where are these 2? Here, you know which one we're doing.
One has label, the other one.
I think you did the label on this one, no? To show? I think this is the one. I think so. Let's try. No, one can stand and one cannot stand. Yeah, but I was trying to put them all the same. So sample leftover. What? Sample leftover 1, sample leftover 1. Neither of them can stand. Then I think this is. This one.
Sample 2?
Yeah.
And sample 1?
Yeah.
But it's like because then we will.
Count here, you can say now. Why
The equivalent methods of just we have
The 1 to 5 saturated phase. Saturated phase.
So colleagues, now we will proceed with the measurements. So wait just a minute. We will prepare for this and show it to you soon.
Maybe can take a little bit of water, but
This one?
What is this one?
yeah, maybe sometimes you do like this. It should be just like a replica spatula.
This is also number 1. So we have a replica. Someone already made them. Yeah, we have to wait. Sorry for the cameras. Nearly finished? I think so. You can, yeah. So you can make it say, I can open it. If you've done it 100 times, you can do it again.
Oh, okay.
We're gonna do that. I didn't check them on. This one I checked. So nice. So do your chest. Yeah. Yeah, good enough. This is sample, right? Okay, now let's centralize it. Let's make it central. 30 minutes. Yes.
Yeah.
How are we going to do? Are we going to measure
So I'm here.
I think that we should sit down again.
So then you and me just measure. Yeah, maybe. I will now make it simple. It's a late question. Do you think we have a marker for that whiteboard?
Oh,
No.
I don't know.
Right.
Well, maybe
Put the number easy in Excel there.
Excel.
Yeah, we can do that.
Do you happen to have a model? So do they have maybe a sponge? I'll still cage you.
What's that?
What time did it start? Yeah, maybe. Maybe we're gonna tell Andres. Do you think I can?
Maybe.
Yeah, no, I think it's possible. Right. Go back to generalized teaching. Hey. Last 15 minutes. Yeah? Okay. First of all, thank you all for your help. Yeah, because of this hybrid stuff, I think it is nicer if we just keep this centralized. We will just measure it. There's nothing to it. You stick a probe into a tube or into the soil. And while we do that, yeah. But first, let me explain what we are looking at. This one, in all the chaos, has been made twice. So even with one, we have a replica. We can see if the saturated phase is indeed kind of standardized, and these are hopefully very close values. And this is the 1 to 2 method that goes with sample 1. Here we have sample 2, saturated phase that we will stick our probe in, and the associated 1 to 2 tube. Now, sample 3, 4, and 5, all the saturated phase with 1 to 2 in between, behind it. And not that it is very relevant, but I've drawn a little graph. I couldn't erase this, but I will just make very big dots that my dots will outshine these blue words. And we can see if there's, at least between these two methods, a nice correlation. Maybe not the most relevant, the correlation between 1 to 2 and an EC probe, but it should, if both of them are kind of reflecting something, they should be kind of similar. One thing I'm noticing already, I've told you something about how quickly things settle and the turbidity. I already see that these 3 samples here, they've all been shaken relatively recently, I'm pretty sure, but the watery phase is already pretty quickly visible. So I'm not really worried just based on this, because I know they're not super pure sand soils. But just based on this, I'm not very worried for water infiltration. But that's a kind of a side thing. So let's measure. I brought my ECE meter. My EC meter, sorry, that's completely wrong to have said the ECE meter. I brought an EC meter. And we have a probe. You have yours? Yes. This one is mine. Well, it's not mine. It's my colleague's Aryan's. I've never used or seen it. Yeah, maybe let's use yours. Yeah. I will use maybe the 1 to 2 there. This one is staying turbid a lot longer, though. Just checking.
Maybe start with those
Start with that one, yeah. And then you do this one with your probe. So this is sample 5, where we had this was the salinaria, these extreme photos of white soils in the sparse, very tolerant but still very suffering halophyte standing there. Okay, but yeah, I can't really show you this, but you have to trust me. If it's very low, the units differ. The units start to change. But this is a very high value. This is indeed what I hoped. I think this is the highest salinity I've ever measured. Yeah, and he had the error. So yes, we did it. This one happens to happen with work with smiley faces. So I have a smiley face now. If it's not stable, you have to shut. But it's happy now because it's stable. And it's stable at 31.4 Siemens per meter, a 1 to 2 solution. And as I mentioned earlier, roughly between 3 and 5, depending on soil type, is the multiplication. So if we multiply this by 3, which is the lowest possible thing for sandy soils, which this isn't, we already get to 90, more than 90. But if we multiply it with 5, and so we're somewhere between 90 and 150. Extremely high. Anyway, I've never measured an EC1 to 2 of 31.7, it says now. And then we should have some water. So what did I say?
Probe can measure.
Maybe let's try. Let's try.
And well, in this field was these halophytes growing just on the wild. So it's like still some plants can deal with this pretty high salinity level.
Yeah, it might not always be that high. We don't know that. This is also not the recommended way of cleaning. Challenging conditions.
How far from where you took the sample?
4-hour drive.
4 hours.
Error.
Still error?
Yeah.
Shit. Well, we're missing the first point in our graph.
So if you are working on this place, you need an expensive meter to know the level of salinity that you are working on.
Do you know what is the max that this one can measure, or yours?
Mine 20.
So yeah, 20 is the max. Okay, so I will write it down. Just these ones are for cleaning. Sample 5 EC 1 is what did I say?
That was that place that I told you that I would love something there.
But it will not fit on our graph. You're measuring the second one?
Yeah.
Yeah, no, but
do it and or just take the desktop now.
This is it's hard not to be in a lab, even though I'm constantly saying you can do this without a lab.
4.6. Yeah, 31.
Not scanning things, those are impossible to understand.
Sample 4.6.
4.6, and then this one for your probe.
More.
3.1. Usually with this probe, I try a few different places within your saturated paste. 3.1, 3. 3.1. Yeah, I'm confident. 3.1 EC probe. 3.1 EC probe. And what was your value again?
4.6.
4.6. So 3.1. Wow, that's a nice straight line. Yeah. And 4.6 here. So this one is sample number 4. So I probably drew the axis completely wrong. This one should have been. Yeah, let me change this to 1 to 3 as a unless more correctly suggested. 1, 2, 3, 4, 5, 6, 7, 8, and this was 3.1, so then this one was there. Let's say next level. No, the probe is maximum EC level it can measure is 20. It was out of its range. I'm cleaning it.
This is the one, and this is also 3.1.
Another replica. Without knowing.
No, it's the
yeah.
Do you want me to put some more water in the tubes?
Okay. You had 3.1. Yes. Mine gives a smiley face, also at 3.1. It's not going to be a beautifully straight line, I'm afraid. 3.1. Sample number 3 we are at. Code 3. Wow, we made a mess. Kind of clean. So sample 3, yeah, was 3.1 by 3.1, 3.1 by 3.1. That's going to be a straight line up. So sample number 3. This is sample 2.
This is number 2, yes. This is why we forced correlations with the orange.
Smiley face at 3.4, I guess. So that's also like, there's more decimals here. Like it says 3.35, but there's no point in 3.36, you know, no point in writing all these decimals. It's not that level of accuracy. No, let's not pretend we do that. That's why I'm rounding off all the time. Anyway, it's set up at 3.3. So I have a 3.3 for number 2.
And 2.5 for me.
3.3. I don't have water cleaning. 3.3 for me. And you had 2.5. That was sample number 2. Sample number 2. This was sample number 3. No, it's looking like a giant mess, but anyway. The AC2 there was more than there. Sample 5.
We can change the scale on the y-axis.
It's going to be a cloud of dots anyway. So
We need water.
water to clean this one a bit. Absolutely. Thank you. You want to keep it working, but it just turns off the light. Okay, this one looks like a bit more interesting values for me. I have 7.7. No smiley face though. Yeah, 7.7.
And I'm close to that, 7.4, 7.5.
That's weird, huh? That's weird. That's okay, yeah.
It's pretty close to 1:1.
It's pretty close to 1:1 actually, yeah. 7.7 is here. No, yeah, I had 7.7. And you had?
7.6. But actually, we didn't let it rest.
No, of course, yeah.
What is that sample? Sample number?
Sample number 1.
So you put down your point there and force the correlation through the origin. That's all right. You can live with that.
Yeah. But it's just based on this one point.
Yeah, so get some more points up there. But
exactly. Some more points here would have been nice, and this is
what it is.
Yeah, it is what it is, of course. And of course, we took a gamble, and it's never perfect and pretty, but
that's giving you a reasonable.
Yeah, reasonable. Yeah, and actually, we have like in there's one of the correlations I showed you. We have to go from an easy probe to an ECE.
Do you want the previous one, Andrea?
And from 1 to 2 to an ECE is multiplied by something between 3.5 usually and 5.5. So it's within the range. Yeah.
These are standard soils. That's the other thing. So there's a soil texture factor also in play.
Yeah, but it's not pure sand. But yeah.
This is the probe result, no?
Yeah.
Okay, we are here. Like 7.
Yeah, so it looks pretty much 1-to-1.
And the other one was the
31.4.
Oh, it was here, no?
There.
The 1-to-2 is what we measured.
Oh, okay, yeah. So, but these are like the samples we were taking in this citrus fruit trees farm. That actually, like the minimum level that we have read is about 2.5.
Yeah.
With the old correlation that we have also from this farm was about a factor 5. Factor 5. For 2.5 would be around 12, 37. Well, this how much will be yielding our citrus if we have a soil salinity of 12.37.
Yeah, according to your FAO Annex 1 threshold slope, there's almost nothing.
Yeah. And it's like we have sample 4. That it's about 3, and those are the fruit trees. Maybe they have a bit more irrigation
what
now.
Fruit? Citrus is also fruit. What?
Well, citrus are we call them citrus, and then you have the fruit trees that are like stone fruits. Or like in this case are like peach trees.
Very sensitive.
Yeah, but. Like we have, like they are harvesting now. Now is the season, and you can just we don't know what would be the target with if the salinity level will be ideal or optimal for the peach trees. But the thing is that you still have pretty good harvest in organic and with this salinity level. Yeah, but that is what farmers in Spain are dealing with, and
I would mulch them. I'd mulch the trees and I'd call them super organic. Because you're using a straw and you're adding to the. I mean, there's benefit. There's marketing. There's a marketing edge there.
Yeah.
You're using, adding to the.
Yeah, it's all organic and so on. Certainly.
Actually, they do it. They incorporate the pruning of the trees.
Yeah.
And they mow it and they put it aside. Like that this farm is irrigated with drip irrigation.
Yeah.
So they try to put it aside and cover the drips on a mulching way.
Yeah. Excellent. But yeah, I think I started the whole thing saying, measuring soil salinity seems straightforward, but it isn't necessarily. I hope this was a bit of a demonstration of that. But yeah, I think this was basically it for now. I hope you picked up something. At least it's fun to to play with water and mud. But yeah, if there's any questions, please ask. Yeah.
Yeah, I have one or two questions. I was wondering, you said always the rotation specific correlations, right?
Yeah.
From a practical point of view, with personal experience, at what scales are you usually doing that? Are you doing that? Like theoretically, of course, the smaller the better, or the location specific the better. But from practical point of view, what are the scales at which you are playing with?
Yeah, that's another thing, it's kind of touchy feel. Like I showed this example with this spatial heterogeneity, in Egypt, and we've seen photos of it in Spain, and I don't know where that photo came from, but if you see based on your weeds, and if your land is nice and level, sometimes it's slopes, and it's kind of, it's also something you're gonna have to learn by experience. Like, okay, here I can take one sample every hectare or half a hectare or something. Or here I can even trust for 5 hectares, but that's pushing it. But and here I have to really divide every hectare into at least 6 subplots, whatever. But you have to go and look how your crops are performing. If it's nice and uniform, the weeds.
I was rather referring to the conversion factors as you determine.
Okay, yeah, no, soil texture is less heterogeneous than salinity in my experience. So texture is usually more uniform within one farm.
But we had that discussion earlier here in this one group. I guess it's not only texture. I think it's like different soils probably have different aspects that would somehow maybe influence the conversion. So the question here was: is there maybe are there key factors? If we have them, then we could kind of deduct the right conversion for the segregation. So that's in order to also not lead into
the salt mix will affect the relationship between EC and the effects on the plants.
So the identity.
Yeah, and so you have to be careful with that. Now I can give you an example. Magnesium. So often if I'm talking about ions, I say to my students, how do you like to dance with your wife or your husband? You like to dance close, or do you like to dance further away, right? So magnesium and sulfate like to dance together, okay? You dissolve magnesium sulfate in water, the osmotic effect is like having half the ions that you would have compared to sodium and chloride. Sodium and chloride like to dance apart. The concept is called the Van 't Hoff factor. But the Van 't Hoff factor is, in effect, the osmotic influence of the ions, okay? Sodium and chloride have a Van 't Hoff factor of about 1.8, 1.9. They are nearly always dissociated. And so their effects on the physiology, their effects on water potential, they act like 2 moles. So 1 mole of sodium chloride acts a bit like 2 moles of osmotic. But 1 mole of magnesium sulfate acts like 1 mole of osmotic. So the answer that I want to give you is that to some extent, the osmotic effect will depend on the salt mix. As you work in an environment and start to get a feel for it, you do need to understand what the salt mix is. And Bas has talked about that. Where I work, if I'm on if I have a shallow water table salinity, it's sodium chloride. But if I have a sodic soil salinity, it's a mixture of sodiums, chloride, sulfate, carbonate, and bicarbonate, and that's much more complex. So I haven't given you an answer to your question, but I've given you a sense of some of the drivers there. So being aware that the osmotic influences may vary depending on the salt content.
So that was, I think, kind of the idea I wanted to get. So because also the papers I'm aware of, they usually report location-specific correlations or conversion factors.
I've talked about this in a book.
So with enough experience I take from your answers, like when I know about the texture, when I know about the salt mix, I may be getting closer to the right conversion than not having done the whole procedure for is that correct? So
yes, but then you have to understand theoretically almost what Ed just explained, and that in practice it takes just of experience what effect the different mixtures have on the plants. How bad is one ratio of the different cations versus another? Yeah.
In California, they use a salt mix, which isn't sodium chloride, because the regional soils of that area are composed of magnesium, sulfate, sodium chloride. You know, they come up with a mix. They don't use just sodium chloride. Where I come from, we use sodium chloride. So the relationships between EC and yield are approximate if you consider that. But for a salt like magnesium sulfate, it could have quite a low, relative to its osmotic effect. It could have quite a low EC, but it doesn't dissociate. Likes to be, if I'm magnesium, you're sulfate, we're not conductive. Whereas sodium chloride, sodium's over there, chloride's over here, they are more conductive. So it's something to be aware of, but don't obsess about it too much. As you get into an environment and start to learn the relationships, and I think Bas is giving you a fantastic example of how to start to learn the relationships, you'll get a sense of that.
Another short question for me. I was wondering what you would consider the better method for the field, like the direct probe at the saturated phase, or the 1 to 2 or whatever solution method, which gives you the most correct conversion also.
I think this is personal. I think we would give different answers. I have a preference for 1 to 2, but I imagine you have for the probe, huh? Yeah. So yeah. I don't know. Yeah, he trusts his probe. I don't know. I had one. I used to have one. I don't have it anymore. But I never really trusted it.
Can I say that if you had soils that were gypsiferous, then I would be using the saturated paste method because the chances of the errors are much reduced. Okay. The problem is that gypsum is sparingly soluble. North of here in the Ebo Valley, they have soils which are 40% gypsum. Right? And so you take a sample of soil and take a sample of soil that's got no other salt in it, and you measure the ECE. You'll have an ECE of 2 decisiemens per meter. EC 1 to 5, 2 decisiemens per meter. EC 1 to 10, 2 decisiemens per meter. Yeah, because as you add more water, you're just dissolving more stuff. And when you multiply that by the factor, you get a quite erroneous solution. So if you have gypsiferous soils, you should be measuring the ECE every time. Yeah.
Yeah, we have the same.
We should wrap up. Yep. Thanks a lot, Bas. Thanks a lot, Andrea, Ed. The morning, I think, was really interesting. Now we're going to go first for a photo at the front of the building all together, and lunch is been offered like yesterday in the cafeteria from the other side, and we should be back starting at 2. Okay, so Goodbye. In less than an hour, 50 minutes.
Yes.